Hello, and welcome to my presentation on climate change in Northeast Siberia. You may be wondering, why Siberia? Well, Siberia is interesting because of this phenomenon known as polar amplification. Basically, the gist of it is that as the climate warms, snow will melt. As more snow melts, the climate will warm more, which will result in more snow melting, and so on and so forth. This is because the snow is reflecting a lot of sunlight, so it's keeping the area cool. So as it melts, the area warms up to a greater degree, and then more snow melts, and so on. Another reason why Siberia is interesting is because there's a lot of permafrost in it right now because it's so cold, and there's a lot of methane in that permafrost. And methane is a very potent greenhouse gas, so it being released could result in another positive feedback loop. And despite all this, there's not a whole lot of literature out there right now on climate change in Siberia, making it an especially interesting topic for research. Data for the following presentation came from the Coupled Model Intercomparison Project, which is basically a lot of organizations around the world came together and said, we need a standard procedure or like format for all this data we're outputting. And they came together and formed this Coupled Model Intercomparison Project. One of those models within that project is the Community Climate System Model, which is basically the model we have here in the US. It's funded by the US Department of Energy and so on. Out of that model, there's one specific scenario called RCP 8.5, which is a business as usual scenario, which means it's a scenario in which the world doesn't reduce its carbon emissions by that much, which may be more or less likely depending on your viewpoint. So first, I wanted to confirm that 1, I was analyzing the data correctly, and 2, that Siberia was actually an interesting place. So what I did was a simple analysis of, I averaged all the change over all latitude and longitude in the area I was studying of Siberia, and I just plotted it against the time. Well, I averaged each year as well. And basically what you see is a fairly linear line, which has, it's changing from -6 degrees Celsius to 2 degrees Celsius, which, is a pretty good big gap, 8 degrees Celsius, which is like 3 or 4 times more than we're currently expecting global average. Also, it's interesting to note that it's going from below, on an average of below the freezing point, to an average of above the freezing point, which means that a lot of snow may potentially be melting here. Now that we've confirmed that there's going to be a significant change with time, we can also examine what the change is going to be with latitude. Now, you may not notice a time change on here, and that's because to get this y-axis, I took the average temperature from the last 20 years of the century, and I subtracted the average temperature from the first 20 years of the 21st century. And that's how I got the delta temperature on the y-axis. As you can kind of see with latitude, so going from south to north, there's going to be a significant increase in temperature change from around 4 degrees Celsius to 6 degrees Celsius at the upper latitudes. This can be contrasted with the change versus longitude, which is like east versus west. You don't really see a linear relationship. You kind of see a suspicious dip, and then like a flat line, and then another dip. And we'll get into more of that, of why that dip may be there later. But it's not linear, so it doesn't seem to be very dependent on longitude as it is on latitude. After confirming that there was a latitude dependence, we decided to take that latitude dependence and break it down into individual months. Because, as things are averaged over the year, you may miss some significant differences between the seasonal changes, which you could expect. You could expect the changes to be different depending on how much snow there is, what the current temperature was like at the start of the century. And this is confirmed when you look at individual months. So as you can see, the spring and summer months are kind of flatline. They're much less their change is much less than the fall and winter months. And so this is interesting. Also, the change in the fall and winter months are like from 4 degrees Celsius to 9 degrees. So that's much greater than the 2-degree change we were seeing when we averaged across the whole year. Another thing that researchers around the world have noticed is that the change in temperature is often also dependent on how high the point in question is. And this is because as you go up higher, there tends to be more snow and greater temperature differences. So we decided to investigate the relationship between temperature change and elevation. And what we found was actually not typical of the rest of the world. So at lower latitudes, as you go up in elevation, you tend to get greater temperature changes because of that snow melting feedback loop. But here, it seems to be the opposite actually, and where, as you can kind of see, there's a general negative trend where as you go up in elevation, you actually get lower temperature changes. And this could be due to temperature inversions in the Arctic, but whatever it's due to, it's certainly very interesting in comparison to the rest of the world. Now, also, when you look at elevation averaged across each longitude, you kind of see a similar increase and dips as opposed to the change versus longitude graphs. So perhaps that weird shape of the change versus longitude graph is actually dependent on this average elevation on each longitude. What we did here was that we saw that we had a dependence on elevation, and previously we also had decided that we had a dependence on latitude. So we decided to combine the two graphs here and see if those two dependencies held up when they were investigated together. And as you can kind of see, there is a general negative trend in each latitude band, and there's still an increase in change when you go up in latitude. So the 50 to 55 band is the lowest, and then you have the 55 to 60, and so on and so forth. But all the bands sort of have a negative relationship with elevation, which is interesting because it contradicts the rest of the world, basically. I would have liked to have also shown you comparisons between the different months, latitude, and elevation all on the same graphs. But at that point, we're getting into way more graphs and way more slides. So I think I'll conclude here with saying that there's some obvious relationships between the month, latitude, and elevation and the temperature change. Longitude does not appear to be that significant in comparison to the other three I've mentioned, except as it relates to the average elevation at that longitude. And the elevational dependence is opposite of what it is at other latitudes, and this bears further investigation. I thank you for listening, and I hope you have a great day.